Okay, I'm Cesare Di Mauro. I work for BMW Group as a principal QA engineer, and today we'll talk about ternary CPUs and systems in general. So first, some common background, because when we start doing the computer science, we know that computers work with the base 2 system, so using just 2 symbols for represent information. And what we can represent with 2 symbols, it's like 0, 1, false, true, off, on, and so on. We can also represent the numbers using a positional system, like our decimal system, but using base 2 instead of base 10, of course, like we saw here. Okay, we encode information in base 2. Basically, we have some common conventions, which we use a lot. What are, for example, it's a bit. We define a bit as one binary digit. So we can have 0 or 1, false or true, and so on. But we can also pack together 3 bits to make the so-called octal digit to have more compact information using just a single digit. And we can also have 4 bits packed together to that's called nibble. With the nibble, we can use base 16 because it's useful for compacting even more the information using 16 letters, basically, for representing information. And then we have the byte, which is defined as 8 bits. How we can encode integers in base 2? Okay, for signed numbers, we are using the so-called 2's complement. We have an example there. We can represent 100 and minus 100 in 2's complements. Then, as we talked a bit before, we can also define use a byte for representing unsigned numbers and signed numbers with the range which you can see there. We can use 16 bits, 2 bytes to represent more information, so bigger numbers, and so on. 32 bits, 4 bytes with billions of numbers which we can represent. Okay, now let's take a look at ternary systems. Of course, they use 3 symbols for representing information. Which kind of information we can represent with 3 symbols? We can represent 0, 1, 2, or we can represent minus 1, 0, 1, false, true, unknown. I mean, there are several possibilities. We can also represent the numbers with a ternary system, like our positional system, our decimal system, just using the base 3 as a power. And then how we encode information using base 3. Basically, with the 3 symbols, we can define the so-called Tryte, which is one ternary digit. And with a Tryte, we can hold information like 0 or 1 or 2, or we can hold minus 1, 0, 1, depending on how we use them. But the cool thing is that using a ternary Tryte, we can encode more information that you expect. Because if you have 3 symbols, you usually expect, okay, it's just 50% more information. No. If you take a look at the information theory, it's a bit more. Because it's 1.58 blah, blah, blah bits, which we can represent compared to base 2. So more information. And if you take a look at, for example, if we take 2 Trytes, then we have 9 symbols available, and instead, if you take 3 bits, we have only 8 symbols. So we have 1 more symbol which is possible to use with using 2 Trytes. Okay, how we represent signed numbers in base 3? There are several possibilities. This is the so-called biased, 2's complements, 3 complements, and another one which is called the balanced ternary. Which I prefer. With the balanced ternary, basically I use minus, 0, and plus as symbols, which are shortcuts for minus 1, 0, 1. And we still can use a positional system, like a decimal 1. The difference, again, is using base 3 and treating minus as minus 1 and so on. So you have an example there with minus, 0, and plus. We can encode minus 8. If you want to take a deeper look at those things, there's a URL at the bottom. Okay, now let's define the equivalent of nibble, the so-called Tribble. For this, we use 3 Trytes put together. So now we can encode the 27 symbols. Why it's cool? Because like for the hexadecimal system, we can use the base 27 in this case. So we have 27 symbols which we can encode using a single digit. So we can compact information more with this representation. There's an example there. If we have to use 20 treats to represent, then we can just use 7 tribbles for representing information. As you can see there, the letters which are used, some letters are missing. There's a rationale behind it. If you are interested, you can take a look at the URL at the bottom. There's an explanation about it. Okay, now let's go to the equivalent of byte, the Tryte. Now it's a bit tricky, because there are several possibilities. We can use 5 treats for defining a Tryte, or maybe 6, 9. I talk about them because there are some things about those choices. With 5 treats, basically we can encode 243 symbols. And if we compare it with the byte, we are losing just some information because there are 13 symbols less compared to a byte. But it's really close. If you take a look at the unsigned numbers and signed numbers that we can represent, it's very close to the byte. Okay, now let's say, okay, we want to overcome this. Let's use one more treat. So we use 6 treats. Okay, and now we have more than 700 symbols, so we can greatly exceed what we can represent with the byte. And then there's also another possibility, 9 treats. 9 treats can be cool because it's a power of 3. So it makes sense for ternary systems. But it allows to encode a lot of more symbols. My personal choice is defining a Tryte as 5 treats because it's really close to the byte. Okay, how we can represent integers in base 3? Okay, we defined 5 treats, which is one Tryte. So there's this unsigned and signed range of numbers which we can represent, and I put as reference 100, so plus and minus 100, because we as human beings we use decimal systems. So when we usually decide to take a data type for representing information, for us it's natural to take a look at the power of 10, which is it relates to. So that's why I put the reference there. So then with 2 Trytes, we can encode around 60K symbols. So the reference for us is plus or minus 10,000. And with the 20 treats, we can encode billions of numbers. And the reference for us is minus plus 1 billion. So it's really close to the base 2, but it's, we can encode a bit less information compared to base 2. Okay, floating points in base 3. I defined the FP20 using 20 treats. Basically, I use 1 Tryte for the exponent. So we have this range of minus and plus 121. But pay attention because this is in base 3. So it means that with this exponent, we can currently represent and encode a wider range of numbers compared to base 2. Another thing, for the Mantis and sign, I use 3 Trytes, which gives us around 6-7 decimals. This is very close to the float 32 in base 2. There's only a little bit less information encodable because the Mantis has a smaller range, but just a little bit, and we have the sign to encode. Similar thing for a floating point with 40 treats, but here I decided to take another representation using just treats, so 7 treats for the exponent and 33 treats for the Mantis and so on, because it more closely matches the floating point 64 bits. Okay, now let's take a look at the Tryte. It's a Terary architecture which I designed. Like many modern ISAs, that's what I personally call N-RISC. Why N-RISC? Because it's not a reduced instruction set architecture. It's more close to a CISC system. Why? Because if you take a look at the risk definition, and there's a URL at the bottom with the paper of David Patterson, when he defined basically the foundations of risk systems. If you take a look at page 2, there are the motivations and also the requirements for risk systems. If you compare them with the current modern risk processors, we can see that the only thing which is left, basically, is the load and store paradigm. Everything else, it's not anymore more or less the same, because modern risks have many instructions. Some instructions are not simple, so they are complex instructions. They also can require multiple cycles to execute, which is against the paradigm of the first risks. And also many of them also allows to have a variable length opcodes for getting more denser code density. In my case, I define the base ISA with 4 trytes, 20 treats, and then I also have some opcodes which use 2 trytes to improve the code density. The tree ISA is feature complete because it has integer support, so scalar basically, FPU vector with SIMD, like any modern processor today. Okay, how the opcode structure is represented. Okay, for the standard base, as I said before, I use 4 tries, 20 treats. Basically, there is support for integer and FPU instructions. Only the integer is implemented currently. And there are optional opcodes for compact opcodes using 2 tries or 3 tries to have even better code density. And for the vector SIMD, basically I use 5 tries. And this way I can represent something, I can use something like masks with SIMD, which is a modern stuff. If you know about Intel AVX 512, you know what I mean. So it's a pretty modern vector ISA. Okay, general specs for this processor is it's using 27 general purpose registers. If you take a look at the risks, usually they have 32, so there are 5 less, but it's not that much. We can deal with it. Not that important. And R0 is fixed to 0. If you try to write on this R0, an exception is raised. R1 is used as a stack pointer when it's needed, and for instructions like push and pop. And R26 is used as a call for the calls, so as a register to get the return address when calling a subroutine. And the registers are usually 20 or 40 trees, depending on the execution mode. We have one program counter, of course, and 1 flag registers, and the architecture itself is a little engine. For floats and vector, I made a decision here to have both shared. Basically, we have the floating point registers, which are the lowest part of the vector register, which is corresponding. And for FPU, there's support for 20, 10, 20, 40, 80 treats, which are more or less roughly equivalent to floating point 16, 32, 64, 128 for base 2 systems. Here, by design, of course, the minimum size for vector registers is equal to the maximum size of the FPU registers, whereas the maximum size for vector registers is it's undefined. It's implementation dependent because you can design how long a vector can be, because the vector ISA itself is variable length and also length agnostic, like many modern vector ISAs today. Okay, which kind of instructions we have with this processor? There are several quaternary instructions. So it means that we can take 3 sources and get a destination. We have ternary instructions, so 2 sources, 1 destination, and binary, 1 source, 1 destination. And for those, there are possible encodings which we can use the quick immediates instead of only the register. Then there are unary instructions using 1 source or just 1 destination. User mode, privilege mode instructions, calls with jump and link, conditional jumps. We have 27 possible conditions instead of 16 with base 2 systems usually. And also special compare registers and jump on condition, which helps a lot on some situations. Then load store. There are several load store instructions, but there's just 1 address mode, a simple one, so we can have a base register plus an offset to reference memory. And finally, we have also instructions for loading immediates and also for building big constants like 20 treats constants. With 2 instructions, they are built. And a special one for building big addresses for calling subroutine, which are overall the address space. So it's pretty much complete. Okay, some words about the ternary instructions, because some of them are really common. Addition, subtraction with carry, with shift, rotate, usual stuff that you can find on modern processors. But what's the difference with the logical ones? Because how we can define, for example, the AND and OR operators for a ternary system? Because we have 3 symbols to deal with. So for the AND, we define naturally like the minimum. So if you have the minus, so -1, let's say, and plus, which is +1. The AND operator in ternary system is basically the minimum value. So we take minus as the result. And for the OR is the opposite. We take the maximum. So we take plus as a result. And so on with the other logical operators. There are also new operators which are available with ternary systems. And if you want to have a deeper look on that stuff, there's a URL at the bottom where that you can find the theory behind. And for binary systems, for binary instructions, it's more or less the same because we have pretty much common stuff. So move, compare, test instructions, but with the logical ones, there's a huge difference because on a binary system, we have just the NOT operator, which is very simple. We know it. But on a ternary system, there are 3 symbols. So what's the problem here? Okay, for minus and plus, it's very simple. No, you just swap them and it's done. But what to do with the 0? We have 3 possibilities there. Now you can just keep it as is, so we leave 0, or we can convert it to plus or convert it to minus. So with those possibilities, we have 3 instructions for implementing the NOT on a ternary system. And also there are other operators which are available with the ternary systems. And if you want to take a look at the bottom, there's a URL which explains a lot of theory again. Then the assembly which are written for the Tryte, basically it supports all the Tryte instructions, but only the integers ones currently. There are support for directives which are very common, like org, equate, set, print, labels, local labels, comments. We can declare constants, storage, and also for the expressions we can use a wide range of operators, binary operators and unary operators. There's support also for decimal, octal, hexadecimal, and binary literals because for legacy reasons. We use them, so it's useful. We can define strings with single quote and double quote. So pretty much a standard assembler. And here you can take a look at some example of assembly code using this assembler. If you have experience with assembly, then you see that it's pretty much similar to what we already worked on. So really nothing different. How I built the assembler, I am using a cool tool which is called ANTLR. You can find the URL there. I think some of you already know it. Because when you want to have to write a parser for a language, what do you do? Yeah, you need 3 different parsers. You need the lexer, you need also a parser for the syntax of the language, and you need also a parser for the AST which is generated. The cool thing of ANTLR is that you can do everything with a single grammar, which is very simple. And another cool thing is that the ANTLR supports Python for generating parsers, so it's a perfect match for us. Here is an example of some part of the ANTLR grammar for the Tryte. As you can see, it's very simple. You can define the output language for the parser. Then the first rule that you define is the main one called. As you can see, it's very simple because it says just, okay, for the main rule, I need at least one of this item. What is this item? It's basically an optional line and a mandatory new line. Then what is a line? It's very simple to define. It can be a directive or a compound instruction, a standalone label or standalone comment. And so on. You can define also other things according to what they mean. The last line shows also an example of how to embed some Python code inside the ANTLR grammar itself. Another tool which I used is ANTLR Works 2 because it's basically an IDE for working with the ANTLR grammars. It's really cool to use it because it can also give us can generate syntax diagrams for the rules. As you can see there's a module rule which is designed. It's very simple now to see how it works, and also on for line and other rules. Okay, and then what's the outcome of the assembler? Well, what the assembler generates? No, it's a ternary system, so we expect that it's a sequence of treats, right? The problem is that, unfortunately, we are using a binary system. So I decided to use a couple of bits to represent the treat. So I convert basically minus 0 and plus in 0, 0, 0, 1, 0, 1, 1, 0 in base 2. And unfortunately, there's a waste of space because the 1-1 encode is not used anymore. So basically, a treat is represented as 2 bits, and the Tryte as 10 bits. And at the very end, what is an object file for this is just a sequence of bytes, as we know. Okay, now for me is the most important one, because testing is really important on when you have also this kind of projects. I need to test the assembler and also the emulator, because I've written an emulator to test the code before going to the physical board. And there are different requirements. So the assembler has two requirements. I want to check if the generated ternary is the one which I expect. And I also want to check if the assembler outputs something on the standard output. For the emulator, this is different, because I want to initialize the emulator in a specific state when I want to test some scenario. I want also to check some conditions which are always met for all the instructions which are run. And that's called the invariance. If you know the AFL language, that's the thing. And at the end of the execution, I want also to check the emulator status, and that's called the post condition, basically. Another thing is for the assembler and emulator, there's a common goal. I want to use the same assembly code for everything, for testing everything. And I want also to support more complex scenarios about testing, but that's I will show you after. Okay, now that's why I love Python. Okay, all that is basically put there in a couple of examples, some two test cases. They are just, as you can see, they are just declarations. I declare what I want, what I expect. So for the first test, I expect this ternary as output from the assembler. The assembler output should be nothing, because I expect nothing. I initialize the emulator with the two R2 and R3 registers with the proper values. And then what I expect at the end of the emulator execution is that the two registers are always keep the same value, so R2 and R3 are still the same. But in this case, this instruction tries to write to the R0 register, so an exception is thrown. And I want to intercept it with this write to R0 exception. The second example is a normal add instruction, so what do you expect? There's an example here for showing the invariance, so we want to always be sure that during the emulation execution, R2 and R3 registers are always the same, they don't change. And in the post condition, same thing, plus now we expect the register R1 is 5 as the result of the addition. Then the program counter is pointing to the next instructions of the code, and the flags register basically is saying, okay, the result was a positive number. Okay, those are a couple of examples. I think it's very simple to define tests in this way with this framework. How it works? Basically, I've written some decorators to collect all the requirements, which I specify. How it works? Very simple. It basically takes the arguments and keyword arguments and put them on the test method itself. And then there's the text executor. Basically, I've written from scratch a completely new test framework for it. Takes those requirements and uses them when they are needed. And also test framework catches exceptions if they are raised, and then check also if they are the expected ones. Okay, and then I also reuse the Python standard features like the docstring, as you saw before. Now I use the docstring for putting the assembly code there. Because I have both the source code for the assembler, and then also with the decorators I have everything defined there. It's very simple and straightforward to understand. And another thing, for testing more complex scenarios, what I did is that okay, after the emulator execution is done and the post conditions are checked, if the test method itself has some code, I execute it, like you can see on the second example with this assert, for testing more complex scenarios. So and then it's quite powerful this way. Okay, there are some limits, unfortunately, for this testing framework, because first, I want to also test the memory status with the invariance and post conditions, and that's something which I have to work on. Another thing, I want to run the assembler in a separate process, because what happens if the assembler hangs, for example, all test execution hangs? That's not good. And same thing for the emulator. What happens if the emulator goes in a loop? Then it blocks all execution. And so for those reasons, I want to use a separate process to control. Then for implementing the invariance, basically I'm using a single step execution of the emulator. But what is the problem? I cannot test the single-step execution itself. So I have to change a bit, something to being able to test a single-step execution. And last thing, the assembler also generates some standard error output, because, for example, when there's syntax error, and currently I'm not able to catch it, so I want to intercept the standard error and collect and check also these results. So some work ongoing. Now some conclusions, because like every technology tool, whatever it is, there's no free lunch, because everything is a compromise, and there are pros and cons for ternary systems as well. So I think as pros, we have better code density because the instructions take 20 trees instead of 32 bits for opcodes. Then we have another thing which is important, is we have better data density because we can represent information, more or less the same information, using less treats in this case. So 5, 10, 20 treats are more or less equivalent of 8, 16, 32 bits of data. Another important thing is that if you create a chip with the ternary logic, it requires much less wiring. It means also the chip area is smaller. If you want to take a look at some information about that, there is a link at the bottom. And overall, it means also that those chips can have better power consumption. On the cons side, unfortunately, there are some things because of course, our software is using binary as a system, so it requires effort to porting to ternary system. Then we also need some encodings, new encodings for ASCII, UTF-8, RGB. I mean, every data structure which relies on binary system should be changed and find a possible solution for a ternary system. Another problem is that our world is binary, so it will be tricky to interface with the binary world. And last thing, in my opinion, since we are using 3 states, I expect the chips will have a lower frequency for execution. Okay, now some reference. If you want to take a look at the theory which is behind the ternary system, there's a URL, the first URL there. There is a lot of information also on how, for example, you implement an adder with the transistors and so on. There's plenty of stuff which is very cool, if you're interested. And then there are some other links because there's a ternary computer system project which was made by a friend, Claudio La Rosa. Basically, he was the guy which involved me on this project. Okay, now a picture of the first ternary computer board. This board is the first prototype, but it's working. More is coming because we are changing a bit according to our new ISA and so on. Okay, questions? I think someone is missing with the microphone. Yeah.
Here.
Okay. He's coming.
Oh, there's a mic, thank you. Phil, thank you very much for this highly stimulating talk. You talked about power consumption of possible chips, and I was wondering what the basic building blocks of these chips would be, because, I mean, classical computers usually have on and off, and all systems I know of which realize ternary things, well, would require superconduction or things like that, so it's not really power consumption friendly. So maybe, do you have an idea? Just
if you take a look at the link which I gave before on the references, the first one also talks about how implementing a ternary system now with our current technology. For the first ternary computer, we just use the FPGA. And basically, of course, we use 2 lines to represent a treat, and we have some logic to convert in a signal like minus 5 volts, plus 5 volts, something like that. So because we just started on this project, so we're experimenting. But we are also making some experiments about using transistors to have 3 states and implementing logical ports, logical gates with the ternary system. So it's still something which is ongoing.
Thank you.
Welcome.
Hi, thank you for the great talk. And I have a question more about of the future of this, well, where it's going to go. So how do you think that us as software developers, will we have to change our mindset when we're going to write software for such a board? For example, will I be able to use Python, or do we need a ternary Python for it because it's better, or because we have to adapt? Or will there be something like a compiler that will transform Python to a specific version, an assembler, for example, your assembler for the board?
Okay, the thing is very simple. It depends on the abstraction level of the language. The more lower abstraction level you go, the more you need to make work for the ternary system, to adapting the software to the ternary system. But if you, for example, we will talk about Python, no? Porting Python to a ternary system. I think that you, as a coder, can have some problem if you take a look at the number of bits or representation for the integers, for example, maximum integer, no, minimum integer, how many bits did you use, also the bytes, no, such stuff, but which is not that common for the code. But if you, for example, write a Fibonacci function, whatever, you don't see any difference because everything is hidden by the Python implementation for the ternary system. So as a coder, I expect, yes, you can have issues with some stuff which is closely related to the binary. Another example, shift operators, no, and, or, that's the thing. But they are just minor stuff. We can survive, and we can handle them very easily in Python. But if you go lower level, C, assembly, then of course it changes.
Hi, thanks for the talk. Could you please repeat the section about the interface you made to the classical assembler? I mean, do you have some kind of a translator from your assembler to the binary translator, or the assembler, or do you have, I don't know, compiler? Or how does it work? Maybe it works on just on the top of the Python, or
this one?
No. Well, there are Python tests to your assembler, I mean ternary assembler, and how do they work?
The assembly is pretty much new. I written it from scratch. Basically, okay, I take an assembly text file where there's the source code for the assembly code, and then I compile it internally to some. Okay, it's binary because I use 2 bits for representing a treats.
So you have some kind of a translator from ternary to the classical one, or how does it work?
Yes,
okay.
It's shown here. Here, I think this one. Because the assembler itself generates ternary numbers, representations. But what I do, basically, when I write the object file to the file system, I convert all treats to a couple of bits.
Okay, I get it. Thank you.
Welcome.
Hello, thank you for the talk. I just wanted to ask you, if, in your opinion, why this is not a real thing yet? Because maybe we have example of a ternary memory, for example, using in internet routers. And from your perspective, why ternary computation didn't take up from maybe from the beginning, and if there are still technical issues around this.
I think the reason is because when computer science started, they use the binary logic, and when you start something, then you write code for it, you have programs and so on. Then basically you bound everything to the binary system. If you think about something different, there's a lot of
Sorry.
Kill it. just to give another example, no? When we talk about operating systems, no? Usually when there's a new OS which is coming, for example, Fuchsia from Google, no? And you go, oh, it's a new OS, no? But if you take a look deeper, no, you see, no, it's the usual POSIX compliant operating system. POSIX is here, I think it's 50 years, which we have POSIX systems. But everything, all research is flat down towards POSIX because it's the standard for the OSs, no? So you don't do any research about something completely new, or it's quite rare. And that's the thing. No, usually when you have a standard which imposes itself, then it becomes the mainstream and the only thing that people that just use and they think about. You don't think out of order. No, can I do something which is really different for solving problems? That's something which doesn't work. Another example is Python, for example. Python, uses the bytecode. But I introduced the so-called word code in, I think, 2005 or 2004, something like that, no? And after 9 years, no, they changed Python using some word code like. But before that, nobody did it. When I started working with Python, with the internals, I said, okay, well, why using bytecodes? If you use the word codes, it can be better, faster, more competent, and so on. But nobody think about it. So it's also a question of thinking out of order. You don't have to stop yourself, and just follow the others, what the others did. You have a problem, you can think about, okay, can I do it something different? Maybe we can have some gain, and that's the thing. So I hope that creating a project like this, like a ternary system, can give the input to other people, to study it, work on it, and maybe in the future we can have some systems which are working as ternary systems, like mainstream stuff. That's the thing. Yeah, but I know, but okay, if else is a bit different. This is condition. But for other stuff, usually we are all flat on the binary. Also, university teaches you everything in binary. Binary systems. There's nothing which gives you some information about other different things.
So we have time for one more question, and then we're going to have to wrap up.
Okay, I squeeze a few questions with microphone, so I'm cheating. First one, you said that you have to think again about UTF-8, ANSCII, and so on.
The encodings.
The encodings. But this would be a great case when we can get rid of all these ASCII, ABCDC, just stick with UTF. And if you code UTF on unsigned Trytes, what's the problem of redefining everything? You just fit, they are unsigned, you just fit all the UTF points and code points, one after the other, and it doesn't matter if it fits on one Trytes or two Trytes, because even with UTF 8, 16, and 32, there are no real boundaries on what putting inside each one. Second question, why you prefer 5 treats instead of 9, which is a pure power of 3. And the last question about Boolean operators, even in Python, they would be great, because if you just work with math, maybe Boolean operation, binary Boolean operation are great, but once you start working with users, and everybody here, I think, has to struggle with GDPR regulation. The idea of having yes signed, no, I don't want to give my permission, or none, there is no, which is quite different from no. None is no information. Nobody took care of asking the user to sign. So having a free state for yes, true, and none, or not done, would be great. For real world, for modeling the real world where someone isn't always yes or no, but there is I don't care, I don't want to answer, I don't know because nobody put me a paper that I had to sign, would be really great.
Okay, just to reply to the last stuff, to the last question. Of course, if you have a ternary system, you can do something like that, no? And for us, it's natural because as human beings, no, usually you can say something which is yes, yes is no, but there's also I don't know. So for human beings, it's very useful having a ternary system. The problem is that this is just a special case because you can have some other case where you can have 4 choices, for example. And then, again, with a ternary system, you have to use 2 treats to represent 4 states. So, depends on the context.
Shades of yes or no are already yes or no in various degrees. None, not available, not submitted.
And no, whatever you want, yes.
Logical and semantic difference from available.
Yeah.
So we need to say thank you to our speaker.
Can we...
And
Okay, thanks.